Hey everyone, and welcome. Today we're diving deep into one of the most fundamental forces out there. I'm talking about that invisible pull that holds planets in orbit and keeps our feet on the ground. So what is this force that literally shapes our entire world?
Seriously, have you ever just stopped to think about it? What is it that's keeping you from floating off into space? And at the same time, what's holding the moon in that perfect dance around our planet? It's like an invisible string, tethering everything together. And this force, it's acting on you right now.
Well, the answer to all of that is actually a single, pretty elegant concept. It's the idea of a universal attraction, a basic rule of the whole cosmos. And it all comes down to one word: gravitation.
So here's the deal, and it's kind of wild. Anything that has mass, you, me, this planet, pulls on everything else that has mass. That means you, right now, are gravitationally pulling on your phone, on the moon, even on stars that are light years away. So why don't you feel it? Well, it's because that pull only gets really noticeable when you're talking about something massive, like planet-sized massive.
And this is where the genius of Isaac Newton comes in, with this absolutely brilliant equation. Now, it might look a little intimidating, but the idea is actually super simple. The force, that's F, gets stronger if the objects are heavier, that's the M1 and M2 part. But, and this is the key, it gets weaker the farther apart they are. And not just a little weaker, a lot weaker. It's something called the inverse square law. Basically, if you double the distance, the force drops to just a quarter of what it was. It's this super fast drop-off that runs the whole show.
Okay, so see that G in the formula? That's kind of the magic ingredient. It's the universal gravitational constant, and it's the same number everywhere in the universe, which is just amazing. The formula also tells us a couple of other cool things about gravity. One, it's a central force, which just means it always pulls straight toward the center of an object. And two, it's a conservative force. What does that mean? Well, think about lifting a book. The energy you use gets stored, and you get all of it back when you drop it. No energy just vanishes into thin air. It's all accounted for.
All right, so that's the big picture, cosmic level stuff. But let's bring it all back down to Earth. How does this whole gravity thing affect you and me every single day?
Right here on our home planet, we have a special name for that gravitational pull. We call it acceleration due to gravity, or if you want to sound like a physicist, just little g. It's basically the constant rate of speed up that anything experiences when it's falling, all thanks to the enormous pull of our planet. And that little g has a number, 9.8 meters per second squared. Now, what on earth does that mean? It's simple, really. If you drop a ball, for every second it falls, its speed picks up by another 9.8 meters per second. It's just this constant, relentless acceleration, pulling everything toward the center of the Earth. Okay, so this brings up something that trips a lot of people up. We all say mass and weight like they're the same thing, but in the world of physics, nope, they are totally different. So let's get this straight once and for all. Let's break this down. Your mass, that's how much stuff you are made of. Your atoms, your molecules, the whole shebang. It's just a number, measured in kilograms, and it is always the same, whether you're on Earth, Mars, or floating in deep space. Now, your weight is a totally different beast. That's the force of gravity pulling on all that stuff. And because it's a force, it has a direction, down. And since it depends on gravity, your weight can change. Go to the moon, where gravity is much weaker, and you'd weigh way less, even though your mass, the amount of you, hasn't changed one bit. You know what's cool? You can actually feel this difference. And you don't even need a rocket ship. Nope. All you need is an elevator. That everyday ride is a perfect little physics lab for understanding the difference between your real weight and your, well, what we call apparent weight.
Just picture it. You step into an elevator and it's standing still. You feel normal, right? That's your true weight. But then it starts accelerating up. For a second, you feel pressed into the floor. You feel heavier. That's because the floor has to push extra hard on you to get you going. Your apparent weight just went up. And what about when it accelerates down? You get that little flutter in your stomach. You feel lighter. That's because the floor is dropping away from you, so it's not pushing up on you as hard. Your apparent weight goes down. So you feel heavier, you feel lighter, but did your mass actually change? Not at all. It's just the forces of motion at play.
So, to wrap this all up, I want to leave you with a really mind-bending fact: gravity. It holds our whole solar system together, entire galaxies, even. It seems so incredibly powerful, but it's actually the weakest of the four fundamental forces of nature, by a long shot. I mean, think about it. A tiny little fridge magnet can pick up a paperclip, completely overpowering the gravitational pull of the entire planet Earth.
an entire planet's force defeated by a tiny magnet. It's a force that shapes the cosmos, but it's also incredibly delicate. Makes you wonder, doesn't it? What kind of amazing balance of forces must be at play to make our whole universe work?